All right, so now we're going to give some thought to cycles, and we got a thing called linear ordering, and this is a thing called a DAG. It's a directed acyclic graph, right? And they're often used for you label the nodes with tasks. And if you know anything about getting dressed, you'll know that it's really good to put your underwear on before you put your pants on, right? And it's good to put your pants on before your shoes on, and it's good to put your socks on before you put your shoes on. Yeah? You want to argue with this?
Yeah. You're going to put on your shoes before you put on your pants?
No, you put on your pants before your shoes. Is that direct direction? Oh, no, it's the other direction here. You put on this side. Put on your underwear before you put on your pants. You put on your pants. Oh, yeah, that is kind of...
I don't get it.
Oh, yeah, you put on your pants. It's the order you have to do them. You have to do your pants before... Oh!
We're talking about topological sort.
Yeah, we're doing a topological sort. Now, actually, did you ask, should you do your pants or your socks first? Is that the question? Well, because my son was so slow at getting dressed. So slow. And he told me one day, all right, so he told me one day that he had a new technique in which he was going to get dressed faster than me. And his technique was that he put his socks on first. And I never quite got how he thought that was going to get him dressed faster, but it didn't. And anyway, here are two different topological sorts, right? And the point is you can put your socks on in various places as long as it's before your shoes. Right? Everybody good? So what is a topological sort? It's a total ordering. This is often called a poset because it's a partial ordering, right? It tells you some orders, but it doesn't tell you a total order. This is a total order. And what we're looking for is a total order that respects the edges. All right? So what we need is for every edge here, the edge from underwear to pants needs to be respected. It needs to be in the right direction. Right? Everybody buy that? So there's one topological sort. And there's my son with his topological sort. And he still didn't get out of bed very fast. All right? Now, of course, if we had an extra edge here, could we make a topological sort? No, because there's a cycle. Right? So, all right, so now we're going to give an algorithm in which the input is a DAG, is a poset, and directed acyclic graph, and the output gives you one valid ordering, all right, to complete the jobs. Because you can imagine you're a factory, and these are all the jobs, and you have to come up with an order to do them, right? And like often, we're going to just do proof by example. All right? So here's our algorithm. Well, first off, who goes last? F or L. And what do we call F and L? Do you have a name for them? They're called sinks, right? A we'll call the source because it has no edges coming in. And F and L we'll call sinks because that's where the water drains, right? Source and sink, right? And they have nobody leaving it. So those are sinks. And so what we're going to do is we're going to find a sink, right? Now you're given a graph. How do you find a sink?
Start from the source, find the top.
All right, that's pretty good, except we don't know where the sources are. But that's okay. You start anywhere, and you look for it. So we're going to put it last, and we delete and repeat. So, but here, how do you find a sink? Well, you start anywhere, and you just walk any direction, and you're guaranteed not to cycle because it doesn't have a cycle, and you're going to bump into a sink. Right? Everybody got the algorithm? Now, the great thing about this algorithm is it has how long does it take you to find a sink is order n, and you have to repeat it n times, so we get an n squared algorithm. Right? Yeah?
What's your opinion on vertices that aren't connected?
You can put them pretty well anywhere.
Yeah.
Where to put them? No, I don't have a preference. We need a total ordering. All right, so instead, we're going to do depth first search. Why? Because that's the topic, right? And it works. So we're going to have a stack, and we're going to do depth first search, and we're going to start from anywhere. We don't know what the source is, right? Choose any node to start from. So I'm going to start from D, and I'm not putting the edges because I was lazy making the slides, but you'll know what we're doing, right? So we got D, we push E, we push G, we push F, right? And now we can't go any further. So what does that tell us? That tells us, great, F is a sink. Where do we put it? We put it on the end, right? So, yeah? What our algorithm is, find a sink, delete it by putting a breadcrumb on it, and repeat. All right? So we found a sink, F, and as we pop F off the stack, we will put it in reverse order. Right? So F comes off, it goes there. Right? Take it off the stack, write it backwards. All right, so now we're at G, so we continue. What does G do? G pushes on L. Right? And now L is a sink. We can't go anywhere, so we push L off, and it goes backwards. Right? So now G's done, so we push G off and put it backwards. And now E's done, we pop it. D's done, we pop it, and we have our thing backwards. Right? Everybody buy that? Now we know we're not done. So start at any node that you haven't seen yet, and repeat. So I goes on, J goes on, K goes on. Now what do? We're stuck, right? Because we don't want to go places we've done before. So K comes off backwards, J comes off, I comes off, and we write them backwards. Right? People follow that? Then we choose another node that we haven't been. B, C, C comes off, B comes off. Then this time we're lucky. A goes on, H comes on. H comes off, A comes off, and now we're done. Right? Everybody buy that?
So node you're chosen is randomly?
Yeah. The new node is a random node that you haven't seen before.
Okay, so I can get a node anywhere. Like I can just choose the A.
Yeah. Yeah, but you don't get to choose it. I'm telling you, the adversary chooses it. So what we're going to try to prove now is, given any graph, given any choices of orderings that you start the nodes and ordering which you follow the edges, it's always going to return a total ordering that respects the edges. Right? All right, so now we're going to prove that, more than less. And in order to prove it, how do you remember first order logic? I don't know if we've never really done first order logic together, right? We want to prove that for every graph, for every ordering that you choose the nodes, we want to prove that what we have is a total ordering. All right? What's the definition of total ordering? Is for every edge ij, it's respected. Right? So how do I prove this? When it's a first order logic, if it's a for all, I say let it be arbitrary. Let my graph be arbitrary. Let my ordering be arbitrary. Let my edge be arbitrary. I'm going to prove that that edge is respected. Right? So I didn't say all of that. I said the last bit. Consider some edge. All right? So here's my edge from U to V, and there's some graph. Right? So let's look at cases. Oops, I always hate it when things come in different directions. But here we go. Here's our first case. The case is when U happens to go on the stack before V does. I'm not claiming that always happens. I'm claiming this is my case 1. Right? And so now U goes on before V goes on. So what's going to happen in the future? Is U going to come off before V goes on? No, because of this edge, V has to go on before edge comes off, before U comes off, right? So because of the edge, we know that V goes on before U comes off. And now what happens? We continue. Who comes off first? It's a stack. V comes off first, then U comes off, and we have the right order. Right, everybody good? All right, that's case 1. Let's go for case 2. Case 2, V goes on first. All right? So now let's have some subcases. Let's say that V happens to come off first, and then U goes on, and then U comes off, and we get the right order. Right? Everybody good with that? Second case. All right, so now let's give our third case. V goes on first, and then U goes on. That was our next case, right? So how's that?
Doesn't that give us a cycle?
Yeah, then when U's on, what we're going to do is we're going to be handling U. And when we handle U, we find V, and V's already on the stack, so that creates a cycle, right? Here we have, what's the stack? Oh, this should be an orange line because it's our stack. Our stack gives us an edge, a path from V to U. And then we have the edge U to V, right? And that gives us our cycle. Everybody buy that? Yeah. Yeah, it would still work. It would still work. Everybody say we looked at all the cases. Right? People.
Case 3 doesn't work for that.
What? Case 3 doesn't work. Case 3 kind of does work. Case 3, you say, dude, there's no answer because there's a cycle. Right? So we're handling all the cases correctly. All right, everybody good? Yep. The case 3 only happens when there's a cycle, right? And we were kind of promised in the precondition that it didn't have a cycle, but somebody let it slip through the cycle, and then we detected it and said, sorry, buddy, you have a cycle, so we don't have to give you any answer. We bail at that point. Yep. Yeah.
Sorry, but when you started from so no, like way before this, but when you started from you picked E first.
Yeah.
You went all the way to F and then you went back. So
Yeah.
Okay, yeah, there. So after D is off, you just pick any other number.
Yeah. At every point when you're done in the stack, and the stack's empty, your goal is choose an arbitrary, in fact, a for all kind of thing. The adversary is giving you the worst case node to start from. Right? I mean, some people use the word random, but for me it's an adversary. If I'm not choosing it, and I'm not doing it randomly, then as soon as I do it randomly, I need to have probabilities. If I don't want probabilities, then I need to say an adversary is choosing it for me. Yeah?
We can also do it with the breadth first.
I don't think so. I think that it won't work with breadth first search. But I've never given it a moment's thought. I was taught this algorithm a billion years ago, and I kind of ran with it. But
Sorry, you can start the other way around. Finding the edge of the control and the other way.
oh, you can turn it all upside down? Yeah, but that would just be doing that first search in the reverse direction.
No, so you know how we find the thing first,
Yeah,
and then we give it out.
yeah,
Start with
the source.
the source, the word next to it.
Yeah, but how do you find the source? You follow the edges backwards.
All right.
I think you're just going to be doing depth first search upside down.